Good afternoon, everyone. So, welcome to my YouTube channel, Maths Abhigram. So, today we are going to see sixth practice set on functions of bounded variation. Okay, it contains 10 questions. These questions are really very important. So, let's start today's lesson now. Okay, in last lecture, we have done some such type of question where the functions were not functions of bounded variation. Okay, we will continue six question of related to previous practice set. Okay, so that you will get some maturity. Okay, more maturity. So fx is equal to x cube cos pi upon x square if x belongs to open 0 1 close, and it is 0 if x is equal to 0. Then option number 1 is f is not differentiable. Second option is f is differentiable, and third option is f is not function of bounded variation, and fourth is f is function of bounded variation. Okay, so what will you do here? We know that this function is going to be differentiable. You can check. So option number 1 is not correct. F is continuous also. You can check that is. So option number B is not correct. We have to check C or D. Either C is true or D is true. So we have to check. Now we have done one derivation in previous practice set. Okay, that x to the power alpha cos pi upon x to the power beta. If alpha is greater than beta, then function is bounded variation. If alpha is less than equal to beta, it is not function of bounded variation. Okay, now we will use that here. Now, so let us start its solution. So what is that fact solution? We know that if fx is equal to x to the power alpha cos pi upon x to the power beta, if x belonging to open 0 1 close, and it is 0 if x is 0. If alpha is greater than 0, so f is function of bounded variation. F is function of bounded variation. F is function of bounded variation if and only if alpha is greater than beta, otherwise it will not be. So now in question, what is given? What is alpha? In question, what is alpha? Alpha is 3 here because x cube is here. What is alpha? Alpha is given in given question. In given question, we have alpha is 3 and what beta is 2. So alpha is greater, alpha is 3, that is greater than 2. 2 is beta. So what does it mean? F is function of bounded variation. So F is function of bounded variation. Which option is correct? Option number D is correct. Okay. Now move to next question. Now this question is given. Same question is only alpha beta values are changed. So this function is differentiable, and you can check this function is all continuous. So option A and B are not correct. Either C option is correct or D. Let's check it again. So what is alpha here? Alpha is 2. And what is beta? Beta is 1. So alpha is equal to 2. And this is greater than 1. 1 is beta. So this implies F is function of bounded variation. So which option is correct? Option number D is correct. Now move to next question. This question. Again, here alpha beta values are changed. So you see that this function is not going to be defensible at 0. This function is not defensible at 0. Okay. So it is not defensible. So option number A is not correct. Okay. So, but this function is continuous. This function is continuous. So option number B is not correct. Now either C is correct or D is correct. Let's check it. So alpha is equal to what is this? 1. And beta is 1 by 2. Alpha is equal to 1, that is greater than 1 by 2. 1 by 2 is beta. So what does it mean? F is function of bounded variation. So which option is correct? Option number D is correct. Now move to next question. Now this question, in this question sign is given, but we have same characterization. We have studied this. If fx is equal to same, you replace cos by sine, x to the power alpha sine pi upon x to the power beta. If x belongs to open, 0, 1 close, and 0, if x is equal to 0, okay, then f is then f is function of bounded variation if and only if alpha is greater than beta. Okay. Now in the given question, we have what is alpha? Alpha is 3 and beta is 2. You see that alpha is 3, beta is 2. Okay. So what we have? We have alpha is equal to 3, that is greater than 2, that is my beta. So this implies f is function of bounded variation. Okay. So which option is correct? Option number D is correct. Okay. Now move to fifth question. Similar question, it is only alpha beta value are changed. So this function is differentiable. You can check. This function is continuous. So option A and B are not correct. Either C is correct or D is correct. So let's check it. What is alpha here? Alpha is 2. And what is beta? Beta is 1. So alpha is equal to 2, that is greater than 1. That is my beta. So this implies f is function of bounded variation. Okay. So the option number D is so sixth question. Here also alpha beta value are changed. Let's check it whether it is function of bounded variation or not. This function is not defensible. You can check. This is continuous. So option A or B are not correct. Either C is correct or D is correct. We have to check whether function is function of bounded variation or not. So alpha value is 1. And what is beta? Beta is 1 by 2. Okay. So alpha is equal to 1, that is greater than 1 by 2. That is my beta. So this implies f is function of bounded variation. So which option is correct? Option number D is correct. Now move to next question. So this question is given fx is equal to upon log 1 upon x if x is x belongs to 0 1 1 by 2 close interval and 0 if x is equal to then option number 1 is given f is monotonically increasing, b option is f is monotonically decreasing, option number C is f is function of bounded variation, d option is options A and C are correct. Let's check it. So if we have x and y belongs to 0 1 by 2 close, then what we have such that x is less than y, then what will happen? Then this will imply 1 upon y will be less than 1 upon x. Okay. If this is happening, but log is an increasing function. Log is an increasing function. Log is monotonically increasing function. Monotonically increasing function. So what we have, log 1 upon y is less than log 1 upon x. Okay. So this implies 1 upon log 1 upon x is less than 1 upon log 1 upon y. Okay. Because if this is okay, you see that. So this implies because these two belongs to of 0 1 by 2. So this is greater than 1 by 2. Okay. So both are, so they will be, so what they have, so they will be because x by can take at most 1 by 2 value, so it will be 2. So what we have, so they are greater than 0. Okay. So they are greater than 0. That is why I can change. So this implies so this is for all x y belongs to 0 1 by 2 such that x is less than y. So this implies 1 up fx is monotonically because f0 at f is 0 at x is equal to 0. So it is monotonically increasing. If it is monotonically increasing, this implies f is also function of bounded variation of which function of bounded variation. So which option is correct? So first option is correct, f is monotonically increasing. B option is not correct. Okay. C option is correct, function of bounded variation, because every monotonically increasing function is function of bounded variation. So D option is correct because it contains option A and C are correct. So option number D is correct. So let's click it right. Is correct. Now next question is A belongs to R and we are taking functions close interval A to infinity. Be a function of bounded variation on each closed interval AB. F is function of bounded variation of closed interval AB for B greater than A. We are putting F B F A infinity is equal to limit of variation F on closed interval AB. Which of the following statement is correct? If this variation is finite, then limit of functions F exists at infinity. If limit at infinity exists, then VFA infinity is finite. So option C is if BFA infinity is finite, if and only limit exists at infinity. D option is none of the above. Let's check it. So it is given that BFA infinity is limit B tends to infinity BFAB. So what does it mean? It means given epsilon greater than 0, there exists M belong greater than 0 such that B F A Y minus B F A X will be less than epsilon for all Y greater than X and this is greater than M. Okay. But this is a positive function. This implies this is what is this? This is B F A Y minus B F A X less than epsilon for all Y greater than X. What is this? This is nothing but B F X Y. Okay. So this implies B F X Y is less than epsilon for all Y greater than X. But this is always less than Fy minus Fx. Because we are taking xy interval. So this implies Fy minus Fx less than epsilon for all y greater than x. So what does it mean? It means limit x tends to infinity Fx exists. Because this satisfies Cauchy criteria. So limit exists. So option number A is correct. Okay. If we are taking that this is finite, then option number, if this is finite, then option number A is correct. Okay. Now move to second, whether second statement is correct or no. Now we are taking this function. Let Fx is equal to sine x upon mod f on 1 to infinity. Now, because this is okay. So f is function of bounded variation on 1 n pi for n belongs to natural number. Okay. Okay. And you check that limit x tends to infinity, fx exists because it is zero. It is zero. So limit exists. Okay. So limit exists. Limit exists. Okay. If f is functions of bounded variation, then I am taking this partition. This partition. What is take this partition? Pn is equal to 1 pi by 2, 3 pi by 2. Okay. Like okay. 1 here I should write pi 3 pi by 2, 2 pi 5 pi by 2. Okay. And now 3 pi. Like that it will go, and it will be n minus 1 pi to n minus 1 pi by 2, and next one is n pi. Partition of n pi, sorry, 1 to n pi. Then what we have? Then what we have? BF 1 to n pi. What is this? This is greater than sine 1 plus one. Okay. And it is 2 upon pi, 1 upon 3 plus 1 upon 5, 1 upon 7, like that up to 1 upon 2 and minus 1. Okay. But this is divergent, and this tends to infinity as n tending to infinity, because this series is partial sum of divergent series. So this implies BF1 n pi tends to infinity. Tends to infinity as n tending to infinity. So this implies BF1 infinity does not exist. Okay, does not exist. So which option is correct? So option A is correct, but B is not correct. So obviously C is not correct because it is if and only if. So if limit exists, this exists, variation exists, but it is not correct. We have checked. So option number, none of the above is not correct because first option is correct. So option number A is correct. So now move to next question. F closed interval a b to r be a function of bounded variation, and there exists k greater than 0 such that fx greater than equal to k for all x belongs to a. Then there exists positive monotonically increasing function g and h such that f is equal to g by h. Second option is there exists positive monotonically increasing function g and h such that f is equal to g by h. There exists positive monotonically increasing function g and monotonically decreasing function h such that g into h. All options are correct. Okay, let's check. Okay. Solution. So fx is greater than and k is greater for all x belongs to closed interval AB. Okay. Okay. So okay. So log you consider this fx is equal to, sorry, you take you take fx is equal to log x. Okay. Okay. So log x is Lipschitz function on any interval k to infinity for k greater than 0. Okay. You can check. This is a Lipschitz function. Okay. Lipschitz function because derivative is bounded, so it is Lipschitz function. Now f is function of f is function of bounded variation. So this implies f is bounded on AB. So this implies there exists there exists k dash greater than 0 such that fx is less than equal to k dash for all x belongs to AB. But it is given that it is fx value is greater than equal to k is positive, so it means what? So this implies, but it is given that, and this is k is greater than 0, so it means f is positive, so I can write like that. So this implies, okay. Now f is equal to log x is Lipschitz on this interval k to k dash, okay, and f close interval AB is contained in this. or f is function of bounded variation as well. F is function of bounded variation on AB. I told a result in practice set, previous practice set. You see that in some previous practice set, you will find if f is Lipschitz function and g is function of bounded variation, then f compose g is function of bounded variation. Okay, so this implies f compose f, that is log fx is function of bounded variation. On closed interval AB. Now, by Jordan, now this function log fx is function of bounded variation. By Jordan theorem, there exists PQ, closed interval AB to R, monotonically increasing functions, such that log fx is equal to p minus q, because log fx function is functions of bounded variation. So this implies fx is equal to e to the power p minus q. So I can write it e to the power p into e to the power minus q. Okay, so I can write it e to the power p upon e to the power q. So this implies f is equal to this. So let's say g is equal to e to the power p and h is equal to e to the power p. P and Q are monotonically increasing. E is exponential functions are monotonically increasing. So this implies G and H are monotonically increasing. Okay. Okay. So first option is correct. So first option is correct. Okay. F is equal to G by H. So F is equal to G by H. So this is A part. Now B. So if G is monotonically increasing, I can write it like 1 upon H, 1 upon G. Now I can say, G is equal to 1 upon H and H is equal to 1 upon G. So this function H G dash and H G, 1 upon H and 1 upon G are monotonically decreasing, because G and H are monotonically increasing. So option number B is correct. B is also correct. One is correct. Option number A is already correct. We have checked. Now, what about C option? So I can write F is equal to G I can write G is equal to, now I can write G into H dash. Okay. So G is monotonically increasing. So here what was that? F is equal to H dash upon G upon G. Sorry, G dash upon G dash upon H dash. Okay, H dash. Where G dash is monotonically decreasing and H dash is also monotonically. Now we move to option C. Now I can write it G into, from here I can write G and H dash. H dash is equal to, sorry, I can write here. This is my G and this is G dash. G dash. So I can, G is monotonically increasing and G dash is monotonically decreasing. So option C is also correct. So option C is also correct, because we can say it G and we can say it H. Okay. So the G is monotonically increasing, H is monotonically decreasing. So all three options are correct. Okay. First option is correct. Second option is also correct. Third option is also correct. So all options are correct. Okay. Option number D is correct. Okay. Now move to last question. Question number 10. Let f be a function of bounded variation, then f may have uncountable number of points of discontinuity. Second option is f have finite numbers of points of discontinuity. F has at most have at most countable number of points of discontinuities. Option number D is none of the above. Let's check it. Okay. By Jordan theorem, f is function of bounded variations. By Jordan theorem, f is equal to p minus q, where p, q are monotonically increasing functions. Monotonically increasing functions. But we know that, but monotonically increasing functions have finite countable numbers of points of discontinuity. But monotone functions have at most countable number of discontinuities. Okay. Discontinuities. Okay. So let's say A is equal to the number of discontinuities of f, sorry, p, and B is equal to the number of discontinuities of Q, then this implies the number of discontinuities of F is contained in the union of A and B. Okay, because the discontinuities of B and G, their union, number of points of discontinuity of A and B will be discontinuity of F. It means discontinuities of F will not exceed the union of discontinuities of function B and Q. Okay, but A and B are countable. Both A and B are countable, or at most countable. So this implies F has at most countable number of discontinuities. Okay. So which option is correct? So let's check. F may have uncountable number of points of discontinuity. Option number A is not correct. Okay. F have finite numbers of points of discontinuity. No. Countable, it has a countable number of discontinuity. You see that greatest integer functions, or you can define this is F is difference of two monotonically increasing functions. P and Q have countable number. Countable means it can have countably infinite also. So finite numbers of points of discontinuity is not a correct option. C option is there is correction. F has, I should write has here. F has at most countable number of points of discontinuity. So this option is correct. D option, none of the above, is not correct. Okay. So what we have done in this question, since P and Q are monotonically increasing functions, so they have at most countable number of points of discontinuity, and F is difference of base functions. So discontinuity of F will not exceed the union of discontinuities of P and Q. So P and Q have countable points of discontinuity, so their union will be also countable, at most countable. So F has at most countable number of points of discontinuity. So option number C is correct. So today's session up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's session. Thank you very much.